Alright, this is another video. This time it is a turbojet engine, 9.79 in the 6th edition. If you want to see the knowns of the problem, just stay here, kind of pause the video, but we're going to get in here because I think this video is really long, so apologies in advance. So first, we're going to start out by trying to find all the values at state A. I write 1 because I used to number it differently, but I figured other people would probably want it to be numbered how they do it, so I changed my ways for this video. Hope you're all happy. Yeah, see? State A. Oh, wait, I didn't do it yet. I go back, I promise. So, that should be state A. So, using the knowns that we were given at the beginning, temperature at A to be 420 degrees Rankine. We know that yep, there it is. There's the old light bulb coming on. And HA to be equal to 100.32. Maybe, man. We're starting off pretty rough today, aren't we? We'll get there. We'll get there. We're warming up here. Sometimes you gotta take the warm-up pants off, the jacket, get running down the baseline. Alright, so PRA is 0.5760. This is just from the tables. A22E at the temperature of T1 or TA to be 420 degrees Rankine. And so we found this. And so using these two values, we can then solve for, or using, I guess, one of the values. This is for the diffuser. Remember, this is A going into the diffuser and 1 coming out of it. So the diffuser energy equation, which we learned in Thermo 1 and haven't really talked about in Thermo 2 all that often, but we do have this equation that I'm about to write out. And so we are solving for H1 in this equation. And so the equation sets up as this. 0 is equal to Q minus W dot plus M times the quantity of H1 or HA minus H1 plus the quantity, or plus VA squared minus V1 squared over 2. That is the basic equation. We know there is no heat or work being transferred. We're just going to say that, and then since that is there, you can get rid of the mass. And so, and we know that there is the diffuser reduces the velocity to a very negligible level. So we can get rid of the velocity at the at V1 or at state 1. And so that is the equation for H1. H1 is equal to HA plus VA squared divided by 2. But since we're in English units, you know English units, they have to do everything the hard way. So H1 is in BTU. I did a little crash course here, just so I didn't have to do it in the rest of the problem. So H1 is in BTUs per pound, right? And that means we are adding, and HA is also in BTUs per pound. So we're adding BTUs per pound to feet squared per second squared. And so we have to convert feet squared to over second squared to BTUs per pound, right? That's the plan here. So 1 BTU is equal to 778 feet pound force, right? And so this is gravity. This is gravity in English units. So we are doing 1 over G, which is 32.2 feet per second squared, is also in part of this conversion. And so I think what it works out as is that those second squareds flip to the top. You cancel out the second squared on the bottom. The feet, one of them cancels down here, right? Let me see. And the other one cancels. So you get rid of the feet, you get rid of the seconds. You're left with pound on the bottom and BTUs on the top, which leaves you with BTUs per pound. Man. And so, since we found H1, we are now going to use that value to, to fix the state of state 1 after the diffuser. And so, state 1, you go to the table and you interpolate, and you get PR1 to be equal to 0.83492. And I think that's all I needed for that. Some of you might be wondering, because you might have experience in doing this cycle, you have to try and the key to doing this cycle, if you don't want to go back, but we're going to go back. I'm going to explain it later, but try and keep up on finding the pressure at every state. It saves you a lot of work in the end, but I'm going to explain that later, because honestly I forgot when I was doing the question, so I did it in the order in which I did it. But anyway, next we are solving for state 2s. This is the ideal case of the compressor, which means we can use relative pressures 2 and 1 to solve for the compression, or I guess pressure ratio, which, as you can see, we were given pressure ratio. We have PR1, which means we can solve for PR2, which is 12 times PR1, and that gets us a value of 10.019. I think, yes. And so, like other, whenever we use other relative volumes pressures, we're now going to use that relative pressure to find all the things associated with state 2s. So that's T2s, H2s, all of those values. Because remember, relative pressures are only the ideal case. And so, we are going to fix state 2s. And so, by looking at the table and interpolating, you can find that H2s is 227.29. And did I do T2s? I don't think I did. I don't think you need it. At least I don't think. I'm pretty sure you don't. I can't see where you would use it. So H2s is equal to that. And so, from that, we are then going to use the compressor equation, efficiency equation, to solve for the unknown that we are looking for. We're looking for something at state 2, normal state 2, not ideal. And so, since we've been doing this all of Thermo 2, anytime we're using cycles and efficiency, if you have the perfect case and the state before it, you can solve for the real case, the actual case. And so eta compressor is equal to H2s minus H1 divided by H2 minus H1. I've done these three videos all back to back. My voice hurts. I apologize. I don't have any cough drops or anything near me. And so, we then, when you manipulate around, you solve for H1 plus H2 S minus H1 divided by the efficiency of the compressor, which I think is 0.88. And you get H2 to be equal to 243.07. Alright. And so, now that we have that, we can move on. So, we know everything about state A, 1, and 2 now. State 3 is really easy. This one was given to us. It was given that we were given the max temperature of the cycle, T3, which was 2400 degrees. And so at 2400 degrees, we can find everything that we need to find using table A22. Is it A22E? Yeah, A22E. And so we know that T3, as I said, was 2400. And from that we can find our H3. Or can't we? Apparently I can. 617.22. And our PR3 to be 367.6. And so, now that we have those, we can then move on to solving for state 4. Now, in this cycle, it's a little different. You solve for state 4, the actual state, instead of solving for the perfect state through the turbine. This one's a little backward, but there's a reason for it. And that's just due to the relationship of the work. Since from the notes or from the lecture, you'll know that for a jet engine cycle, the work of the turbine is equal to the work of the compressor. This cycle's goal is to not make work. It's only supposed to power the compressor. So, we know the work of the turbine equals the work of the compressor. Due to a series of like diversions of air, it always equals up to be the same. Like whenever this is the goal. And so, basically, it only takes on the mass that makes these two equal. The mass flow rate moving through it, that is. And so, since we have this setup, we know that we have H3, we have H2, and we have H1. So you can solve for H4. H4 is equal to H3 plus H1 minus H2. And so, using that, we found H4. This is the real state. And so the real state, 485.7, is H4. And I think I was about to write down PR4, but that doesn't make any sense. So there is no PR4 for this one. Because this is not an isentropic process. Because we know that the turbine has an efficiency that isn't 100%. And now, this is the difference. We're now using the turbine equation to solve for the ideal state, not the real state. Just a little difference in this cycle. It'll all become clear why we're doing this in a second. That's if I explain it well. No promises. And so, using this equation, so turbine's efficiency for this cycle is H3 minus H4 divided by H3 minus H4s. We're solving for H4s. That is the perfect case of expansion through the turbine. I was doing some math here. I was trying to or some algebra, moving things around, but I didn't do it very fast. Count Mississippis until I figure it out. Do me a favor and don't and count them long. And so we find that H4s with an efficiency of 90%, I think is the turbine. You get 471.09. I think I end up writing that in a second. Yeah, I do. I'm very generous. Man, write it. Have you waiting all day. So, moving on to the next part. Oh, if you can hear that, that's my cat. He likes to sit outside my door and meow. He made himself a part of the video now. So now we're using H4s to fix state 4s. And so by doing that, we are trying to find all the values associated with 4s. So T4s. No, from the table. Yeah, I guess I'm make that clear. And so T4s, let me see if I can find that. 1878.134. And PR4. Oh, yeah, and PR4, I guess, but I just wrote 4s here, but it'd be PR4 is equal to 240 or 135.246. And now, this is where the pressure thing came into play. I mentioned earlier that you have to, as you do this question, you should be trying to find the pressure at every state. And the reason being is because if you don't do that, you'll get to this point and you realize you can't solve it. Because you don't know the pressure, because you have to do the diffuse or the nozzle. And if you do an isentropic nozzle equation, it's P5 over P4 is equal to PR5 over PR4. Well, you don't know PR5, right? And you don't know P4 either if you haven't been going through the question. You know P5 and you know PR4. So you have to go back and solve for all the previous, or you have to solve for the pressure. Because we're trying to solve for PR5, right? Which gives us H5s. And so this is the problem. As I just explained, this is where you end up running into problems. So let this be a lesson. Even for me, I forgot to do it during this when I was doing it on hand, so I decided I'd just make a example out of myself. You'll realize that you do not have 4 or PR5, so you cannot solve that. So we have to solve for all the unknowns, which is P4. Well, P4 leads you to get PR5. But to solve for the actual pressure of 4, you have to go back and solve for all the previous ones. So you have to solve for pressure 1, 2, 3, and then 3 gets you to 4. So, yeah, tough break. But if you find all the pressures before you get to this state, you can just solve the question. But I didn't because I'm old and washed up. So, this is just state A, right? We're trying to find pressure 1. So, you know the relationship, P1 over PA is equal to PR1 over PRA. And so you get P1, because state A is a perfect, perfect expansion through the valve. Yeah. Or no, it's not expansion, is it? I can't remember which one it is, but it goes through the valve isentropically, so you can use PRs. And then for the compressor, we know the compressor's ratio, which is 12. So that means that P2 has to be 12 times higher than P1. If it wasn't that, it's not a compressor. So, yeah, P ratio is how I denoted it earlier, I think, but I just wrote that out because I don't want to confuse anyone more than I'm already confused myself. And so, I don't think I had this one on hand, so I had to calculate it. Apologies. It's hard to talk for 2 hours. I could never get into public speaking. So, P2 is equal to 156.6 if you just manipulate that equation. So now we have P2. And so now P2 and P3, that is across the combustor. and there's no pressure change across the combustor, so P3 equals P2. Give me a second to write it out. I'm a slowpoke. And apparently OCD. So, now we solve for the pressure of 4. And so, how we solve for pressure of 4 is the similar ways that we've been solving for the other ones. P4 over P3 is equal to pressure ratio, or PR4 over PR3, right? We know PR4, we know PR3, and so we can solve for P4. Wow, I didn't do a very good job at that one, did I? Yeah, it's as best you're getting, I think. So, you get P4 to be equal to 57.5916. Or, well, I was reading those as... Let's try that again. 57.59 pound force per inches squared. Man. What am I drinking? One sec. Nope, it's water. That's not the reason. So, then we solve for P5S. And so P5S is solved for using that equation I wrote earlier. I think it was like 3 slides earlier, but I'm going to write it again. I'm not going to do that to you. We know P5 equals P1 because the pressure of 5 is going to atmospheric, because it's going through the nozzle and it's back out in the atmosphere, so you know its pressure is back to original state, which is 1. And so we have the equation PR5 over PR4 is equal to P5 over P4. But when you manipulate to solve for PR5, you get the following. 23.635 is PR5. And I'm doing some things. I guess I'm thinking again. That's dangerous. I don't know what I actually can't remember what I'm doing here. What I'm doing on the screen. If it isn't clear, I'm voiceover, guys. I'm not doing this live, so I couldn't remember what I was doing about an hour ago when I did this. So, yeah. So, PR5. So we're using PR5 to find H5S and I guess T5S. I guess you could find, but I don't think you need to. And so we have H5S is 289.9. And so now we are solving the problem. We finally made it to the solution to the problem. If you guys are still alive out there, you've made it to the end almost. Don't collapse on me now. I know it's hard listening to me drone on about this, but it's necessary. And so, we are now solving for the heat into the cycle. Which is H3 minus H2 times mass flow rate. We have a mass flow rate given in the problem as 85 pounds a second. But the question wants this, of course, make it difficult, in BTUs per hour, I think. And so we have to change it to BTUs per hour. And so this is where I find all my old values. I had to kind of look across my paper. And so Q into the cycle. I think I write it first in BTUs per second, and then I change it to hours. Yeah, I was trying to find the least confusing way to do this, since I didn't have that one handy, but I think I ended up just going on there and doing it on my calculator really fast. Because sometimes I don't solve the question in the way that it asks, but then I have to do it afterward anyway. So, just in case there's some Hawkeyes out there that go and find the question and say, well, you didn't put it in the right units. I want to avoid that conversation. So, you get QN to be 31,802.75 BTUs per second. And then you multiply by 3,600 seconds in 1 hour. And then you get, then you get it into hours. And that ends up being 1.145 times 10 to the 8th BTUs per hour. That was a long process, wasn't it? And so the next part is asking for the pressure after the expansion through the turbine. All that means is just pressure 4. Whatever the pressure is coming out of the turbine. 3 went in, so 4 has to come out. And so we just have to find, I think we found it already. We had to, right? You had to have found the pressure to solve for this point. So you just go back, and I think I end up writing it to just be pressure 4 is equal to 57.59 psi. This question was just trying to give you breadcrumbs. It was just trying to lead you towards the answer if you couldn't solve, because the next part, or the final part, you can't solve for unless you did that. All the other answers you could get without doing that. The part that long pressure, finding the pressure at each one. You could get every answer except for the final one without doing that. So this part, work of the compressor. So we know work compressor is equal to mass flow rate times H2 minus H1. And these are just values that we have. So you can just plug these in. And you get, oh, well, I actually wrote it out for you. Once again, what a nice guy. Maybe, well. It's like my answers are a Where's Waldo. Maybe I should write them in white and red ink. How would the white ink work though? That wouldn't. Never mind. I'll just give them a little red stocking cap. All my answers. So you get work of the compressor. Obviously, we once again have to change this into BTUs per hour. That's what the 3,600 is for. So you get 4.024 times 10 to the 7th BTUs per hour as the work of the compressor. And now the final part is looking for the velocity at the exit. This is what the whole cycle is trying to get. We're trying to get this, the fast velocity at the exit. And so this part, this one's a little tricky, especially since in this question the nozzle has an efficiency. Most of the times it wasn't. This was the only question I think I've ever done that had an efficiency of the nozzle. But I'll show you how to tackle it just in case you ever get one. I don't think you will, but the book didn't really have many choice options for this sort of question. So, the efficiency of the nozzle we have to write the nozzle energy equation, which is the same as the diffuser, only different directions of, or different numbering, I guess you could say. So this is the nozzle equation. And so you know those three go away. And you're left with V5 squared, if you move that to the other side, and V4 goes away. I don't know if I wrote that, or if I got rid of that. But yeah, V4 goes away because then inside the cycle, in comparison to the outside air, it's very small. So therefore, you don't have to worry about it. So what I did here was I multiplied the 2 to the top and have 2 times H4 minus H5 and move the V5 squared to the other side. Right? But remember, this is the perfect case. We're using H5S here. That should be H5S. Right? So we have 2 times H4 minus H5S. And remember, this is units again. But only this time, this is velocity equals, not BTUs, or this isn't BTUs equals. So you just bring it to the top. What you did before, remember you divided by 778 and 32.2 before, you just bring that to the top. It's just the inverse of that. You're turning BTUs per pound into velocity, not velocity into BTUs per pound. So just flip it to the top. And so, if you do that, you end up getting the following answer. The 3132.125 feet per second. Now, that is 5S. That's the perfect case for the nozzle. The real nozzle is V5S times the square root of eta nozzle, which is 0.92 in this case, I think. Yes, 0.92. And so 3132.125 times, and the reason it's square rooted, I mean, you could have just put eta nozzle inside of that other equation, the one I did up there, and you would get V5, but I just didn't, just to show you the difference between the two. And so you get V5 to be equal to 3004.23 feet per second. And that is the exiting velocity of the nozzle. That's what we're after. Alright, well, thank you guys for watching. I hope this cleared a lot of things up for these types of questions. As always, hope you learned something, and see you on the next video.